can mix with other things with charges, because charges can attract one another. Things without charges, like nonpolar covalent, can only mix with other nonpolar covalents. So again, that's the top paragraph of the drawing dissolving how-to sheet. Dissolving process requires a solvent and a solute. Those are two terms that we're going to go over in the notes at the end of the hour. Although water is what's considered an excellent solvent, and typically ionic compounds are solutes, but there can also be polar or nonpolar solutes. What we're going to go over in this drawing dissolving how-to sheet are the steps 1, 2, and 3, how to draw out things being dissolved. So step number 1 says draw the Lewis-Dot structure for each compound. Indicate the charges on ions and partial charges. So right above number 1 it says follow the steps below to draw the dissolving of water with lithium fluoride. The water Lewis-Dot we should have done on the previous activity. Here's the Lewis-Dot for water. Lithium fluoride is an ionic compound. So we still have to know how to do Lewis-Dot drawings. Lithium would be a +1 ion. Fluoride would be a -1 ion. So this is step 1. Step 2 on this how-to sheet says redraw the Lewis-Dot structures so that the opposite charges are next to each other. With polar covalent molecules, the more electronegative atom will be the partial negative end. In other words, water has charges, partial charges, but it has some sort of charge. Lithium fluoride has charges. These charges can attract one another. So, lithium fluoride, the lithium part, would be attracted to the partial negative of the oxygen on water. The fluoride part would be attracted to the partial positive, the hydrogen end. Now, when dissolving occurs, what I'm trying to show in this picture here is that there's oppositely charged particles. There's an attraction right there. There's an attraction right there. You don't actually have to draw the dotted lines. When it's an ionic compound, water will actually break apart the cation from the anion. Notice how in my previous slide, lithium fluoride is stuck together due to oppositely charges. But when you put an ionic compound in water, they usually will break apart into their two separate ions. Step 3 of this how-to sheet is trying to have you draw what dissolving would look like. And what it says is, draw multiple solvent molecules, in this case water. When dissolving, solvent surrounds the solute. If this is an ionic solute, the cation and the anion are separated from each other. If it is a polar solute, the solvent will surround the partial charges. So, if lithium fluoride is being dissolved in water, since it's an ionic compound, the lithium and the fluorine will separate from one another. Then water will surround each ion. Here, for example, is water surrounding the lithium ion. Notice how I drew all 3 of my waters, with the oxygen end next to the lithium. Reason being, the oxygen end is the partial negative end of the molecule. Oppositely charged particles attract one another. For the fluoride, it would be the hydrogen end, because that's partial positive. Drawing the dissolving of substances is something that we do need you to do. Your homework is going to be 3 questions of doing this. Hopefully it's a real nice, quick, easy homework. The lab that you're going to be doing next time is going to have you draw dissolving of things as well. If I were to grade a drawing dissolving problem on right or wrong, I would look at, first off, if it's an ionic compound, are you separating out the Li from the F? And here's my Li. Here's my F. Did you separate them? Because when you dissolve an ionic compound in water, they break apart into their cation and anion. Secondly, did you put multiple waters around each particle? Usually that means 3 is what we're looking for. Third is what I'd call orientation. Yes, you put a lot of waters around the lithium, but is it the partial negative end of the water closest to the lithium? Now this is how you draw the dissolving of an ionic compound in water. That's what this how-to sheet goes over. This how-to sheet does not go over what if it's polar covalent. What I'd like to do is a quick problem on here that goes over that as well. So this isn't on the how-to sheet, but let's say we have hydrogen fluoride. Hydrogen fluoride is a polar molecule. Fluorine being the most electronegative element on the periodic table would be the partial negative end. The hydrogen would be the partial positive end. Remember that line that I drew between the H and the F? That line is a covalent bond, a sharing of electrons. Covalent bonds do not get broken when you put them in water. In other words, the H will not break apart from the F. Instead, what will happen is water will now surround. I'll draw the water in blue. Draw another one up here if I wanted to. So if it's a covalent compound, you don't actually break apart that covalent bond. An ionic compound is just particles held together by opposite charge. Those can break apart when you put them in water. A polar covalent, it doesn't break apart, but it still gets surrounded, because in the dissolving process, things get surrounded. Orientation still matches up. The partial negative end of oxygens are attracted to the partial positive of the other particle. Partial positive of water is attracted to the partial negative of the fluoride. On your homework for tonight, you are going to have to do a problem where you're drawing the dissolving of an ionic compound, like I did with the lithium fluoride here. You're going to do a problem where you're going to draw the dissolving of a polar covalent compound. What if I put a non-polar covalent in water? Like oil, for example. Oil's a non-polar molecule. How does oil and water intermingle with one another? Do they mix? A lot of people are shaking their heads no. Oil and water don't mix. If it doesn't mix, there must not be any type of charges for water to attract to. And that's why you'd have a layer. So if you're ever asked to draw the dissolving of 2 things that don't mix, usually you have the Lewis dot of one thing on the top here and a different thing on the bottom here because they don't mix. What you're going to see in the activities that we're going to be doing at the lab bench in a few minutes is that idea of some things are able to mix and some things are not able to mix. So I just wanted to go over what you'll see on the homework then with that as well.